In this video, we're going to walk through an example of ANOVA from start to end. So go on and pause the video, read this section, and get familiar with the problem that we're trying to solve. Coming back, so we've got three different waxes that we're looking to solve, and we're trying to see which one deteriorates differently and which one is going to be the most effective. So the most effective in this case would be the one that deteriorates the least or last the longest. So our factor in this case, we're comparing three different waxes. Our factor is car wax, again the overall name of the variable. We've got three levels, 1, 2, and 3. The experimental units in this case, well, we don't have people here. Again, that's the one I normally use in social research. But each experiment, what are we doing the experiment on, and what's being randomly assigned to type 1, 2, and 3? Well, the car is being randomly assigned to 1, 2, and 3, or at least the car when it goes through the car wash. And then the response is going to be the number of car washes. So we're running it through car wash, and we're seeing how many times can I run it through a car wash and the wax still lasts. So in this case, we have the three different groups. This is one way to organize our data. This is the wide organization. The long organization would have a single column called wax that would have entries like type 1, and then a second column called number of car washes that would have an entry like 27. So the second row might have type 2, 33. The third row might have type 3, 29. So that would be the long format. This is the wide format. That's just fine. We have the sample mean and the sample variance. Now, the textbook calculation, when they do the calculation for the groups, uses the sample variance, and that's fine. So that's what we'll demonstrate here, but you can absolutely use the formulas that we wrote out by hand, the more classic ANOVA formulas, where you take each of the data points, you subtract it from the mean, that's what gives you the sum of squares within, and then you take each of these group means and you subtract them from the grand mean and square that. That's what gives you the sum of squares between. So you can do that as well. For our null hypothesis, we have that all three, the mean number of car washes that the wax lasts for the three brands is the same. And then the alternative hypothesis says, well, no, it's not the same. At least something is different within here. Calculating this out, so for the grand mean and a balanced design, so that's a good vocabulary term to jot down. The sample sizes are all equal. The vocabulary term for sample sizes are equal in all of the factor levels is called a balanced design. So in a balanced design, we can just, to find the grand mean, take the mean of all the group means. So group mean 1, 2, 3, add them up, divide by 3, and that gives us the grand mean value. The sum of squares treatment, again, we add up over each of the groups, and then we add up within each of the groups. Now, if we add up a constant within each of the groups, we get 5. So that's why you're seeing this 5 times in front of each of that. In any case, add up the difference between the group mean and the grand mean squared for each one of those, get 5.2, and then you divide by the degrees of freedom. Remember, that's k minus 1. So if k equals 3 groups here, k minus 1 equals 2, so 5.2 over 2 gives us 2.6 for the mean squares treatment. For the sum of squares of the error, again, the textbook formula is a little bit easier than the one we wrote out in our notes, so absolutely feel free to use that. You can also use a little trick if you want to. We'll talk about that maybe later on, where you find the sum of squares treatment and then you subtract. So actually, I'll just jot that down. Sum of squares error. This tends to be the harder one to find, but if you find the sum of squares treatment, you just take the total variation. Because the sum of squares, I'll use TR for treatment. Because the sum of squares of the error plus sum of squares of treatment equals sum of squares total, you could subtract the sum of squares treatment from the sum of squares total, get the sum of squares error. So if we calculated the sum of squares total and then subtracted 5.2 from that, that would give us the sum of squares error of 33.2. So we wouldn't have to do this equation. But when we have the sample variances from each of the groups, it's not too bad. Again, much easier than the formula we wrote up by hand. So I like this one. It's in our notes. You're welcome to look at that on the previous slide. But for the sums of squares of error, we take the k minus 1, or excuse me, n minus 1 for each of the groups, which is 4 for each of the groups, and multiply that by the variance for each one of the groups, and we get 33.2. And our mean squares error we divide by capital N, or the book's notation is N sub capital T, so the total sample size, that is the number of the total number of cars in everything, all the groups, etc., minus the number of groups. So 15 minus 3 is 12, which is the degrees of freedom for our error, and the mean squared error is 33 over 2. This is our estimate, by the way, of the sigma squared, the total error, that epsilon term in our model. All right, so for the p-value approach, again, we're looking for a p-value less than 0.05. For the f approach, we'd use the f distribution with k minus 1 is the numerator degrees of freedom. So remember, MSTR is on top, so we use the numerator degrees of freedom. And the denominator degrees of freedom, that's capital N minus k, or N sub t minus k, as the denominator degrees of freedom. We hunt that down in our f distribution with our type 1 error rate, in this case 0.05, and that gives us 3.89. That's our cutoff. If our test statistic is bigger than 3.89, we fail to, or we reject the null hypothesis. If reject null, if test statistic bigger than 3.89, and if it's not, we fail to reject. That is, we don't have enough evidence to conclude that there's a difference. So calculating out our test statistic is very low in this particular case. P-value we find is bigger than 0.10. They calculated in Excel. It's probably the same as R. Of course, all these use the same formula, so of course it's the same as R. But Excel, we've got a p-value of 0.42. So we fail to reject the null hypothesis. That is, we don't have enough evidence to conclude that there's any difference in the means. So it doesn't look like there's a difference in the treatment types, the different types of car wax, as far as we can tell. And thinking about this practically, so the statistical claim is there's insufficient evidence to reject the null hypothesis. So that's the stats claim. This is a little bit more common sense, insufficient evidence to determine that the mean washes for the wax types is not all the same. But even more practically, like, what is the takeaway message here? Well, think about if you owned a car wash and you were actually doing this. What would your takeaway message be? Well, my takeaway message, if I actually owned a car wash and was doing this, would be that if there's not really a difference between the three waxes, then I probably want to use the cheapest wax, because it's not going to make a difference in terms of how long the wax is going to last, but it'll definitely make a difference to the cost for me. So that's how I'm looking at this particular problem. All right, for the ANOVA table, I plug in my different components. Now, ANOVA tables are the traditional way to represent ANOVA. So if you're ever asked to do an ANOVA, you're going to create an ANOVA table. If you look up a statistical study or something that uses an ANOVA, you expect to see this ANOVA table as part of the results. Typically, you'll see that we have the sums of squares that we calculated, the degrees of freedom that we discussed, and then the mean squares. Note that the sum of squares treatment and error add to the sum of squares total, and the degrees of freedom treatment error add to the total degrees of freedom. We don't do anything with the total for the mean squares or the f or the p-value. F, recall, is just literally dividing 2.60, the mean squares treatment, divided by the mean squares error 2.77. That's literally how we calculate f. And a p-value came from plugging this into R. We could use the pf command to calculate the p-value for the f distribution. We give it this test statistic, then we give it the top degrees of freedom and the bottom degrees of freedom, and we tell it that we want lower tail equals false. That is, we want to look at the top end of the distribution, because that's what was shaded in on our picture in a previous slide, and that will calculate out this p-value. All right, so in the previous one, we did a experimental design, but again, we can do this with observational designs too. That's just fine. So for the experimental design, we can make a conclusion that the wax doesn't cause less less wear and tear, or we didn't have enough evidence that the wax caused less wear and tear on the car, or that the waxes had a different rate of deterioration. In this particular case, for observational, we're just looking at the number of hours per week for the managers. So in this particular case, we've got 3 different plants, and we're observing the hours per week. We're not assigning individuals to city. Now pause and consider why that is. So actually take 10-15 seconds and think this through. Why are we not randomly assigning here? So coming back to this, I hope you've thought through it. I hope it's making sense why you're not randomly assigning in this particular case. You're actually looking at this and well, of course, how could you randomly assign here? I can't take well, I guess you could. I guess you could take a manager and ship them to the proper plant if you wanted to. So take 15 managers and randomly ship them to the different plants, but that's not worth it probably for this experiment. So we're just observing the managers who are already at these plants. We're not randomly assigning. In this case, our factor is the manufacturing plant. The levels of the factor are the different locations of the manufacturing plant, or you could call them manufacturing plant 1, 2, 3, however you keep them straight, but the 3 different plants. The experimental units, who are we actually getting data from? These would be the managers, and again, they're not randomly assigned here, but if we were doing an experimental design, would randomly assign manager to the treatment level. And then what are we looking at? Well, we're looking at the hours worked. This is the outcome variable, the response variable, the dependent variable, you'll hear it called, all those things. And now we do the same formula. So actually go on and pause the video, give this one a shot on your own, and see if you feel up to putting together this ANOVA. It's going to look exactly the same as what we had before. So pause and give it a shot. All right, continuing on. So we've got our null hypotheses. We've got the different numbers of hours. Not all population means are equal is our alternative. The null is that they're all the same. And then we've got the plant managers. Again, instead of mu1, 2, and 3, I tend to like doing maybe mu sub b, mu sub p, and mu sub d to keep track of the different values. Doing our calculation, I get the grand mean to be 60. The sum of squares at treatment, I calculate out to be 490. And then dividing that by the degrees of freedom, I get the mean squares at treatment to be 245. And we're using a 0.05 type 1 error rate. Sums of squares at error, I calculate out to be 308. Dividing by the degrees of freedom, I get 25.6667. And then the F ratio, which is dividing the mean squares treatment divided by the mean squares error, is 9.55. That is, our treatment, our signal, is 9.55 times stronger than our error, or our white noise. Now, if we're building out our table, sometimes we have p-value on the side. Actually, software is always going to put p-value on the side. So if I just ran this in software, this could be something that's come out. Actually, you should be able to construct all this table. Constructing an ANOVA table is absolutely fair game for a test. Just like the problem we just worked through, that would be absolutely legit to ask on an exam. The construction of a p-value would require a computer. So again, I plug in this 9.55 into PR. I give it the numerator degrees of freedom as df1, the denominator degrees of freedom as tf2, and the lower tail equals false because I want the upper tail, the area in the upper tail, and that gives me this p-value. So after computing this, I find the p-value is less than my alpha cutoff. So because the p-value is less than my alpha cutoff, we reject the null hypothesis. That is, we have enough evidence to reject the null hypothesis. That's the StatC conclusion. The a little bit more practical conclusion is that we have enough evidence to determine that the mean number of hours per week is not all the same, and we can. That's a good takeaway message. That the average number of hours worked per week by the managers is not necessarily the same at all of these plants in this particular study. So that's a good takeaway message here. Now that we know that the average number of weeks isn't the same, one question that can come up is, well, which ones are different? And this is a fantastic question. So I've got 3 different plants. I know the average number of weeks for the managers are different. Well, it'd be really important for me to know which one is different. And is it different, like, is one of the managers working a lot more? Is one of them working a lot less? Are they all 3 working different amounts? Those are really good questions and really important to ask. So in the next video, we're going to actually jump into that using a procedure called multiple comparisons, where we're going to compare all the managers to each other and figure out which ones are different and how.